The Navy Product Data Initiative is a cooperative effort by the Navy and the shipbuilders to specify the requirements for and stimulate the implementation of product data systems based on an open architecture having suitable functionality and enterprise-wide interoperability to support affordable naval ship design, construction, and lifecycle support. There are two objectives for this presentation. The first is to provide an overview of the development of a specification for the configuration management functionality of an integrated product data environment. The second is to compare and contrast the configuration management of product models at the part level and the document level. This presentation is a product of the Specification Working Group of the Navy Product Data Initiative. The first part of this presentation will review the tasks, purpose, vision, scope, status of the Specification Working Group as of April 2007, and present an outline of the Navy Product Data Initiative specification. The second part is a walkthrough of a scenario that illustrates the need for configuration management at the part level. The Specification Working Group has been tasked to develop a specification that defines key performance requirements for those elements of an integrated product data environment, focusing primarily on the product data management capabilities, with interfaces to computer-aided design, computer-aided manufacturing, computer-aided engineering, enterprise resource planning, and catalog systems. Current and past efforts relevant to product model data and the configuration management of product model data have been researched. These include efforts made by the Navy Industry Digital Data Exchange Standards Committee and ISO 10303, the standard for the exchange of product model data. The scope has been defined, the initial outline of the specification has been developed, a scenario to illustrate part-level configuration management has been developed, and a website has been created to facilitate collaboration during the development of this specification. The next step is to continue mining information and to concentrate efforts on drafting the configuration management section of the specification and begin to develop drafts of other sections of this specification. The vision is to be able to deliver more capable ships at a lower cost with improved design-build cycle time and with a significant reduction in the cost of changes. We expect the cost and developmental risk to be reduced for each program because by utilizing a spec-compliant IPDE system, the resources required to develop and maintain the IPDE can be spread across multiple programs and shipyards. Design-build cycle time will improve as information will be readily communicated to various participants using best-of-breed software, and by reducing the cost of change through the elimination of non-value-added labor. Configuration management, change management, collaboration, in-service support, and interoperability are within the scope of the Navy Product Data Initiative. Configuration management addresses access control and various levels of configuration units, including class, flight, hull, system, assembly, and piece part. Change management addresses status and dependency management. Collaboration includes the definition of requirements to allow all disciplines to work in the same product model in context of the other disciplines. Requirements for planning, ILS, construction, design reviews, and interfaces will also be considered. Interoperability includes defining minimum data element requirements of various objects at the application level, the requirement for data exchange using standards, and the requirement for an open architecture. DoD security levels, single sign-on, workflow management, how the IPD is implemented, complete functionality of computer-aided design, computer-aided engineering, enterprise resource planning, product data management, and parts catalogs are out of scope of this project. The main sections of the specification are purpose, scope, vision, acknowledgments, and an executive summary. The specification includes requirements for open architecture, configuration management, change management, collaboration, in-service support, and interoperability. The appendices for the specification will include a glossary defining the various terms used in the document, as well as references and sample scenarios illustrating the requirements defined within the requirements section of the specification. The rest of this presentation illustrates the need to be able to configuration manage the product model at the piece part level as opposed to a document level. The example used to illustrate the problem is a simplification of a small portion of the fuel oil and transfer system of the TWR-841. The torpedo weapons retriever was selected because the drawings, product data, and associated data are freely available and approved for public release with unlimited distribution. During this presentation, we will examine a single pipe run as it evolves over several years in a class of 8 ships. In order to explain the issues, a relatively simple example is necessary. This example is limited to the product model of the pipe run and does not show collateral impact on other systems, components, or spaces. Nor does it show the impact on items derived from the product model, such as analyses, work packages, and manufacturing instructions. Each change is implemented as soon as it is accepted. There is no consideration of the workflow or approval process. The collaborative relationship between disciplines and between shops is not considered either. For the purposes of this presentation, the following terms have been defined. A part is an item that is defined and managed by a catalog. A part instance is a part that has been placed in the model. These two terms are used interchangeably in this presentation. Configuration management at the part level is referred to as parts-based. Configuration management at a level of a group of parts is referred to as document-based. Typically, document-based implies a file-based management system, and part-based implies a file-independent database-driven management system. In the document-based approach, multiple parts are configuration managed in a single document. This is the traditional approach to configuration management in the current design engineering systems. Each unique configuration is represented in a separate document. A change that applies to more than one hull must be duplicated in multiple documents. This requires more labor to make a change to the class because each change must be repeated in the various document versions. A mapping of document versions to applicable hulls must be made to determine which document corresponds to each hull configuration. In the parts-based approach, each part is configuration managed separately, which eliminates the need to manage duplicate data. While the parts-based approach has been used for configuration management in execution systems for ship construction, it typically has not been commercially available in systems used for design and engineering. The parts-based approach utilizes hull effectivity to identify which parts make up a particular hull configuration and allows the operator to dynamically build the necessary views. To illustrate this approach, if a user wants to work on the current Hull 1 configuration, the operator defines a query, which will be run against the database to extract the necessary parts from the database, and the system dynamically displays the appropriate versions of the pipe detail for Hull number 1. If the user wants to see the current Hull 5 configuration, the operator would modify the query to reflect the appropriate hull. The query would be run against the database to extract the necessary part instances from the database, and the system dynamically displays the appropriate version of the pipe detail for hull number 5. This slide shows when the various ships in our example are built and modified, as well as what changes are applied to each hull. The details of the changes will be described over the next several slides. In the first year, hulls number 1 and 2 are built to the initial design. In the second year, change number 1 is introduced and applied to hulls 3 and 4 during the construction phase. In year 3, change number 2 is introduced and applied to hulls 5 and 6 during the construction phase, and applied to hulls 2, 3, and 4 as a ship alt. In year 4, change number 3, which is a class change, is applied to hulls 7 and 8 during the construction phase, and each of the other hulls as a ship alt. In year 5, change number 4 is applied as a ship alt to hull number 5 only. In year 8, change number 5 is applied as a ship alt to hulls 1, 2, and 3. In the first year, a pipe run in the fuel oil transfer system is designed using a hose gate valve, straight pipe pieces, and elbows. This pipe run will be butt welded to an adjacent pipe run. At the end of the first year, the class design has been completed and the first two ships are built and designated Hull Number 1 and Hull Number 2. In the second year, a design change is made to address a space constraint problem. A new construction process allows the pipe pieces and elbows to be replaced by a piece of bent pipe. Replacing those parts with a single bent pipe will reduce the cost to construct the system because less welds are required. This change is made in time to be incorporated into Hull Number 3 and Hull Number 4, both of which are currently under construction. This change will also be incorporated into all follow ships. Hull Number 1 and Hull Number 2 will not be retrofitted with this design change. At the end of the second year, Hull Number 1 and Hull Number 2 conform to version A, Hull Number 3 and Hull Number 4 conform to version B. During the third year, a change is made to an adjacent pipe run. In order to accommodate the change, a decision is made to replace the butt-welded joint with a slip-on flange. A decision is made to apply this change to hulls Number 2, 3, and 4, and to incorporate it into the design of all future ships. The change will not be made to Hull Number 1. A ship alt is required to change hulls Number 2, 3, and 4, and an engineering change order is proposed for hulls Number 5 and 6, the two ships currently under construction. Configuration management is now getting a little trickier. The flange needs to be added to the version A configuration to accommodate the change in Hull Number 2. The flange needs to be added to the version B configuration to accommodate the changes in hulls Number 3 and 4 and all follow ships. As a result, there are two new versions, C and D. Version A no longer applies to the as-maintained Hull Number 2, but is still valid as the as-built representation, a lead yard responsibility. Likewise, version B no longer applies to the as-maintained hulls Number 3 and 4, but is still valid as the as-built representation for these hulls. During the fourth year, a class change is made which is applied to all hulls. The change involves replacing a gasket. Hulls 1 through 6 require ship alts, while hulls 7 and 8 are built to the new class design. The gasket needs to be replaced in the version A configuration to accommodate the change in Hull Number 1. The gasket needs to be replaced in the version C configuration to accommodate the change in Hull Number 2. The gasket needs to be replaced in the version D configuration to accommodate the change in hulls Number 3, 4, 5, and 6. This version is also used to build Hull Number 7 and 8. As a result, there are three new versions, E, F, and G. Version A no longer applies to the as-maintained Hull Number 1, but is still valid as the as-built representation for hulls 1 and 2. Likewise, version C no longer applies to Hull 2 and is obsolete. Version D no longer applies to hulls 3, 4, 5, and 6, but is still valid as the as-built representation for hulls 5 and 6. In the fifth year, a mission change for Hull Number 5 requires the addition of a strainer and for the pipe to be rerouted around a newly installed piece of equipment. The rerouted pipe and strainer need to be added to the version G configuration to accommodate the change in Hull Number 5. As a result, there is one new version, H. Version G no longer applies to Hull Number 5, but is still valid as the as-maintained version for hulls 3, 4, 6, 7, and 8. In year 8, the last year of this scenario, the fuel fill valve in hulls Numbers 1, 2, and 3 shows signs of premature wear. Since the hose gate valve is no longer available, it is replaced with a hose bib, flange, gasket, and gate valve on hulls 1, 2, and 3. The new gate valve, hose bib, flange, and gasket need to be applied to the version E configuration to accommodate the change in Hull Number 1. The new gate valve, hose bib, flange, and gasket need to be applied to the version F configuration to accommodate the change in Hull Number 2. Likewise, they need to be applied to the version G configuration to accommodate the change in Hull Number 3. As a result, there are three new versions, I, J, and K. Version E no longer applies to Hull Number 1 and is obsolete. Version F no longer applies to Hull Number 2 and is also obsolete. Version G no longer applies to Hull 3, but is still valid as the as-maintained version for hulls 4, 6, 7, and 8. This is an illustration of the various hull configurations at each point in time. The number of parts required using the document-based approach versus the piece part-based approach over time is shown also. The details in this slide are too small to be read easily. However, a high-resolution wall chart is available. Each column represents a single year in the life cycle. The bottom row contains a description of the changes that are being made at that time. The next row up lists the piece part base configuration units along with corresponding part counts. Above the piece part base configuration units are graphical displays of each hull configuration at each point in time. At the top are the document-based configuration units and corresponding part counts. You should notice that the part counts for the document-based approach begin to grow much more rapidly than the piece part-based. This is significant because when a change is made to a part using the document-based approach, it needs to be made in several locations, whereas when a change is made using the piece part approach, it only needs to be changed in one location and the hull effectivity defined accordingly. The green background indicates an addition to that configuration unit at that time period. The red background indicates a deletion to a configuration unit at that time period. The gray background indicates the configuration unit is no longer the current version. The X indicates the configuration unit is obsolete. Now let's review each change in the context of the document and parts-based approaches. For version A of the design, there is virtually no difference between the document-based and the parts-based configuration management process. At the end of the first year, both processes require 8 instances of 8 parts to define the system and manage the configuration of the class. At the end of the second year, 2 different versions are required to define 4 hulls. Hull number 1 and hull number 2 conform to version A. Hull number 3 and hull number 4 conform to version B. Configuration management becomes a little more complicated because 2 different configurations are being managed. The document-based configuration management process requires 2 models having a total of 12 instances of 12 parts. The model copy results in 3 duplicated parts. The part-based configuration management process requires 9 instances of 9 parts. At the end of the third year, 3 versions are required to define 6 active hulls. Hull number 1 conforms to version A. Hull number 2 conforms to version C. Hull numbers 3, 4, 5, and 6 conform to version D. The document-based approach requires 4 separate models. One of the models no longer reflects an active ship, but is required for design history of the as-built configuration. The document-based approach required the same change to be performed on 2 models, resulting in 13 additional duplicate parts. The parts-based approach just required 1 additional part with the appropriate hull effectivity. During the 4th year, a class change is made. At the end of the 4th year, 3 versions are required to define 8 hulls. Hull number 1 conforms to version E. Hull number 2 conforms to version F. Hull numbers 3, 4, 5, 6, 7, and 8 conform to version G. The document-based approach requires 7 separate models, 4 that no longer reflect an active ship, but are required to maintain design history. The document-based approach requires the same change be performed on 3 models, resulting in 21 additional duplicate parts versus the 1 additional part with appropriate hull effectivity using the parts-based approach. At the end of the 5th year, 4 versions are required to define 8 hulls. Hull number 1 conforms to version E. Hull number 2 conforms to version F. Hull numbers 3, 4, 6, 7, and 8 conform to version G. Hull number 5 conforms to version H. The document-based approach requires an additional model with 4 more duplicated parts, in addition to the 11 new parts required by both the document and parts-based approaches. At the end of the 8th year, 5 versions are required to define 8 hulls. Hull number 1 conforms to version I. Hull number 2 conforms to version J. Hull number 3 conforms to version K. Hull numbers 4, 6, 7, and 8 conform to version G. Hull number 5 conforms to version H. The document-based approach requires the same change be performed on 3 models, resulting in 27 additional duplicate parts and 3 additional models. Using the parts-based approach, only 1 change is necessary, with hull effectivity applied at the piece part level. We have stepped through the 5 changes in our scenario and have compared and contrasted the different part counts and configuration unit counts that need to be maintained between the document-based and the parts-based approaches. Change number 5 will now be used as an example to illustrate the level of effort required to manage the configuration of the product model. Remember, in change 5, the hose gate valve is replaced with a gate valve, gasket, threaded flange, and hose bib. In the document-based approach, the 4 new parts need to be instanced separately for each of the 3 configurations. However, in the parts-based approach, the 4 new parts are instanced once into the product model, and the hull effectivity is defined accordingly in the database. Let's first look at making this change using the document-based approach. This is a sample engineering work order which defines the change and the hulls to which the changes apply. In the document-based approach, the hull effectivity is applied at the document level. To make the change for hull number 1, we need to bring up the configuration of hull number 1, which is version E. Once completed, this will be saved as version I. The gate valve is removed from the configuration. The new gate valve is instanced. The gasket is placed. The threaded flange is added. Finally, the hose bib is instanced. The document is saved, and the document hull effectivity table is updated to reflect the new document version I applying to hull number 1. At this point, the change has only been made for hull number 1 in the document-based approach. To make the change for hull number 2, we need to bring up the configuration of hull number 2, which is version F. Once completed, this will be saved as version J. The gate valve is removed from the configuration. The new gate valve is instanced. The gasket is placed. The threaded flange is added. Finally, the hose bib is instanced. The document is saved, and the document hull effectivity table is updated to reflect the new document version J applying to hull 2. At this point, the change has been made for hulls 1 and 2 in the document-based approach. To make the change for hull number 3, we need to bring up the configuration of hull number 3, which is version G. Once completed, this work will be saved as version K. The hose gate valve is removed from the configuration. The new gate valve is instanced. The gasket is placed. The threaded flange is added. Finally, the hose bib is instanced. The document is saved, and the document hull effectivity table is updated to reflect the new document version K applying to hull 3. At this point, the change has been made for hulls 1, 2, and 3 using the document-based approach. The next several slides illustrate the parts-based approach. This engineering work order is identical to the one we saw in the document-based approach. It defines the change and the hulls to which the changes apply. Using the parts-based approach, this same change request can be used to reduce the complexity and repetitive user actions. The information in the change request is used to define the work content or query. The query is run against the parts-based database, which returns a filtered parts list meeting the query criteria. The parts-based approach uses this filtered parts list to dynamically display the configurations required to accomplish this change. The result of this query is the overlay of hulls 1, 2, and 3. Now that the user has defined the work content from the engineering change order, and the system has dynamically displayed the associated configurations, the CAD operator uses normal modeling techniques to incorporate the changes. The hose gate valve is removed from the configuration. The new gate valve is instanced. The gasket is placed. The threaded flange is added. Finally, the hose bib is instanced. The operator then saves the changes. The parts-based system uses the work content that was defined at the beginning of the user session to update the filtered parts list. Using the parts-based approach, the changes are stored in the database. This change was accomplished in the parts-based approach for all 3 hulls simultaneously by instancing each of the components once. In contrast, the
The document-based approach required the operator to perform the same instance operations repetitively for each configuration. This additional labor is compounded when you factor in the creation of downstream products, such as drawings and manufacturing data, and processes, such as design review and approval, for each configuration. This scenario was limited to a single pipe run in a class of 8 hulls over an 8-year time period. It was limited to some bill of material and geometric data changes. It does not include the impact of these changes on all of the other downstream products. The picture taken in the engine room shows some areas of the ship are pretty dense, containing numerous pipe runs, structure, and other disciplines. The changes discussed in this scenario do not represent the volume of changes that occur for a ship class. To help put this in perspective, a recent class of 5 large auxiliary multi-purpose supply ships, which are not as sophisticated as either a combatant or submarine, averaged 150 class changes a year. Even with all of these simplifications, this scenario still demonstrates the inefficiency and complexity of the document approach versus the parts-based approach. This basic change scenario using the document-based process illustrates the negative impacts associated with the ever-increasing data duplication across multiple documents. The part count rapidly increased to 4 times the actual number of parts with only 8 ships. Even more important is the fact that the labor required to effect change increases rapidly over time as a result. When different document-based models are created for each product configuration, every class change must be made in each different document. In addition to the designer having to make the change in each document model, the checking, reviewing, and approval of each change also needs to be performed for each and every document model. The effort to manage the correct configuration of data using the document-based approach quickly cascades when considering system interfaces, drawing sheets and tech pubs, bill of materials, attribute changes, pipe spool sketches, work packages, flow analysis, structural analysis, schematics, manufacturing plans, and NC data. Remember, this scenario only addressed a portion of a single pipe system in a space. A real ship class will have hundreds of such systems in each area or zone and over 1,000 systems for an entire ship. The high cost of changes using the traditional document-based systems has resulted in the product models not being maintained for the ship's life cycles. These issues also inhibit technology insertion in the ship class. The benefits of the parts-based configuration management approach include the elimination of data duplication by managing change at the part level. This in turn reduces redundant, non-value-added effort required to effect change. Parts-based management allows for dynamic assembly of part views including hull-specific applicability, integrated design, system design review, and work package graphics. There are significant issues to be resolved with the parts-based change management approach. One is the lack of vendors and products supporting parts-based configuration management. Another is the requirement for authoring tools to have an open architecture to enable cross-vendor parts-based configuration management of product model data. This presentation provided an explanation of a document-centric approach and a part-centric approach to product model data configuration management. The advantages of the piece part approach was illustrated using a simplified example. The Navy Product Data Initiative technical team has come to the conclusion that the piece part approach is the way we need to go for efficient configuration management. Configuration management of the product model at the piece part level will be a requirement of the Navy Product Data Initiative specification. For more information about the Navy Product Data Initiative, contact the NSRP Program Administrator at the Advanced Technology Institute or the NSRP Program Manager at the Naval Sea Systems Command.